today we're going to be looking at an algebra review of concepts that's going to be very important here now in chapter 9. Okay, so in the guided note packet, the very first page, you should see this Algebra 1 review. So we are going to be reviewing concepts such as radicals and doing some more with factoring. Okay, so those are the concepts that we're going to see. So this first page is what you should see in your guided note packet. All right, so we want to simplify. Anytime we're talking about a radical, what we need to be thinking about is because it's a square root, well, square means 2. We're looking, we're looking for 2 of the same number. Okay, so what we really want to do when we are looking for simplifying is we want to make a factor tree. So 112 needs to get broken up into 2 numbers that multiply to it. Now, there's a lot of different ways that you can probably break up some of these numbers, and it doesn't really matter how you get started. So the fact that I know that 112 is an even number, I'm going to break it up by putting that it's 2 times 56. Once again, you could probably pick a different or a bigger number, like 8 goes into it. There's a whole bunch of different ways. But once you start breaking it up, I want to circle any number that is prime. So notice that 2 is what we call a prime number. I cannot multiply a number except for 1 and itself to get me 2. But 56 is not a prime number. I can divide 56 and I can break that up. 2 numbers that multiply to 56 would be 8 and 7. 8 is something that I can continue to break down. However, 7 is another prime number, so I'm going to circle it. 8 can get broken up into 4 times 2, where 2 gets circled. Anytime I circle a number, notice how that branch is what I consider dead. I can't go any further. I can keep breaking up 4 into 2 and 2. So essentially, now that I've got my factor tree and I notice that I can't extend the branches any further, what I'm going to do is I am going to put all of those numbers that I have circled back underneath the radical. So notice, count them carefully. There's 1, 2, 3, 4, 5 numbers. So it looks like there are 4 2s and 1 7. And so you can always double check. If I was to multiply all of those numbers back together, it should get me 112. Okay, by taking and putting all of those prime numbers back under the radical, what I want to look for are pairs. I want 2 of the same number. So notice that I have not 1 pair, but I technically have 2 pairs of 2. So that means any pair gets to move outside of the radical. So I have 1 pair of 2s, so I get to write that 2 outside of the radical. I have another pair of 2s, so another 2 gets moved outside, but the 7 wasn't paired up, so that stays underneath the radical. Essentially, the numbers that get to move outside, you want to multiply those together. So 2 times 2 on the outside tells me that 4 is the number that goes on the outside, and 7 is the number that stays under the radical, and that is my simplified answer. Okay. Another way that you could go about doing this is that you could look for what we call perfect square numbers. So really quick, another way that you could have done that, when I have 112, if you start thinking about perfect square numbers, like 4 is a perfect square because that's 2 times 2. Notice that in this case, 112 is actually divisible by 16. 16 times 7 is going to get me 112. 7 is a prime number, which notice that that is going to be underneath the square root. But then notice that 16 is 4 times 4. So here I could have done it this way too. There's a pair of numbers right away. So remember, like I said, a pair moves outside. And so that's why a 4 ends up on the outside. So several different ways that you could go about doing that. You could break it down to all of those prime numbers, or you could go through the route of, do you have a big perfect square number that would then be inside or breaks down that number that's on the inside. Okay, same idea with the second one. We have 5 times the square root of 18. So we have to understand that 5 is on the outside. That's going to stay on the outside. But 18, I want to break it down as much as possible so I can start looking for pairs. So one way you can think of this is, okay, well, 18 is 9 times 2. 2 is a prime number, so that's going to get circled. That branch is dead. Notice that 9 is 3 times 3. Those are also prime numbers, but notice that they are two of the same number. And so we have a pair. So like I was talking about, anytime you have a pair, you get to move that number to the outside. So the 5 was already on the outside, but now because I have one pair of 3s, I get to move a 3 to the outside. The only number that's not paired up is that 2 that we then keep under the radical. So that means I get to multiply the 5 and the 3 to give me 15. So 15 root 2 would be my simplified answer. Okay, in these next couple problems, notice that we are dealing with some operations, adding and subtracting square roots. Now, in order to add or subtract, underneath the square root, you need to have the same number. So notice that in the first example, 3 root 5. So 5 is under the square root plus 2 root 45. So 5 and 45 are definitely not the same number. So I want to try to break them up so then I can end up simplifying each of those radicals to get the same number underneath. Well, if you notice that the 5 underneath that first radical, that's a prime number. The only way to multiply to 5 is 1 times 5. So that means I'm not going to be able to break that up. And so that 3 root 5 is going to stay as it is. But since I can't break up the 5, I'm hoping that I can break up the 45 and get it where I end up with a 5 under the square root. So that means that, okay, can I multiply 5 times something to get 45? And the answer is yes. 5 times 9 is 45. And so that 5 can't get broken up any further. But remember 9, well, that's what we call a perfect square. It's 3 times 3. So when I have a pair, that means that we get to move that pair outside of the radical. So that 3 root 5 that started my problem stays as it is. Notice how there's a 2 outside to begin with, and now I get to move a 3 outside, and those get multiplied together. The 5 that didn't get broken down needs to stay underneath the radical. Okay, I can go ahead and multiply the 2 and the 3 on the outside of that second term, and that's going to give me 6. And now notice that we have the same number underneath that square root. So these are what we call like terms. It's kind of like if this was 3x plus 6x. Notice that means because they have the same x, you keep x and you just add the number in front. Okay, so it's the same idea with the radical. I add the numbers in front, so 3 plus 6 is going to give me that 9, and then I keep the square root of 5 as it is. Do not add the 5s. So that ends up being my final answer. Okay, if I look at the second example there, we've got negative square root of 2 minus 3 root 8. If you look at the square roots, we do not have the same number underneath, which means that we need to break something down and try to get the same number. In the first radical, 2 is a prime number. I cannot break that down any further. However, I can break down the 8. 8 is 4 times 2. 2 gets circled because it's prime. Notice that 4 is 2 times 2. So notice that this time I have 3 2's, but I need a pair in order to move them to the outside. So I have one pair of 2, but then I still have a 2 left over. Okay, so if you need to, think of that negative as like a -1. So we have a -1 root 2. I still have that minus 3, but now my one pair of 2's moved to the outside with that other extra 2 still staying underneath the radical. So I have -1 root 2. -3 times 2 would give me -6, and that still has the square root of 2. And just like the last example, now these have the same number underneath the radical, so I just need to combine the numbers in front. -1 minus 6 is going to give me -7, and then I keep the square root of 2 as it is. And that would give me my answer. Okay, these next two problems deal with multiplication and division. When you are multiplying, it doesn't matter. It happens to be where these two numbers have the same thing underneath. They both have a 12, but it honestly doesn't matter if the numbers were the same or different. When you multiply, you are going to multiply the outside numbers together, and then you multiply the numbers together underneath the square root. So essentially, there's really a 1 in front of that first radical. So 1 times -5 will stay -5. What I like to do then is then I write the square root, and the numbers that were underneath, once again, they don't necessarily have to be the same number, but I'm going to write it like this, 12 times 12. Now, I technically could multiply them together, but it might be easier if you're looking for pairs. Okay, so notice that in this case, I already have a pair right off the bat. If I didn't have a pair, then I could break down those smaller numbers, so then I could start looking for pairs. Okay, if you want, you can multiply them all together, but then you'd have to do a factor tree, which essentially then you'd break it down just like you originally had. But in this case, because I have the same number underneath the square root, remember that gets to move outside. So I'll have the -5. That 12 gets to move outside. And notice that there are no other numbers underneath the square root. That means my final answer is not going to have a square root anymore. Okay, so -5 times 12 is going to give me then -60 as my final answer. So I just cannot stress enough, you don't necessarily have to have the same number under the square root when you are multiplying. Okay, now let's look at this division problem. So when I'm dividing, what I need to do is I need to make sure that I'm never going to have a square root in my denominator. So the first thing I would actually do, though, is I would look for perfect square numbers. Because if you have a perfect square, then you could simplify that right away. And then once again, we never want square roots in the denominator. So we'll have to do something to get rid of them if that's still the case. So if I look at the square root of 4 divided by the square root of 5, hopefully you notice that 4 is actually a perfect square. Remember, that's 2 times 2. So I do have 2 of the same number. So really, I'm dealing with a 2 in the numerator and a square root of 5 in my denominator. 5 is a prime number. It doesn't have any perfect squares. So here's what we have to do in order to get rid of that radical. Kind of like my last example, notice that when I multiplied those two numbers underneath that radical together, when they ended up being the exact same number, my square root disappeared. So that's the same concept that we have to think about here. How am I going to get that square root of 5 to disappear? Well, I need to multiply it by another square root of 5. Because once again, notice that then I can multiply those numbers underneath the same square root. I have a pair of numbers, so that means that the radical disappears because that 5 moves outside. Okay, so here's the thing. If I multiply that by the bottom of the fraction, I have to multiply it by the top as well. When we multiply fractions, we're multiplying straight across. Because the 2 is not underneath the square root and the 5 is, then we keep the 2 on the outside and we keep the 5 underneath the square root. Okay, if the 2 was under a square root, well, then we would multiply the 2 and the 5 and keep it under the square root. So make sure you know that you only multiply the numbers together if they're both under a square root, or you multiply numbers together if they are both outside of the square root. Okay, so that leaves us still with that 2 root 5. Notice the last thing I have to do is I have to look to see if I can simplify. The 5 in the denominator does not have a square root. I also have a number in the numerator that doesn't have a square root, that's 2. But if I look at 2 and 5, there's nothing that they have in common. So that means that 2 root 5 all over 5 would be my final answer. Okay, let's move on to the second concept, which is factoring. Okay, so if I ask you to factor each completely, the very first thing we need to do is we need to look for a GCF. That's always step number 1 when you are factoring. Remember, GCF stands for greatest common factor. So I'm looking to see what's the biggest thing that they all have in common. So between a 2 and an 8, hopefully we notice that 2 is smaller, and I can multiply 2 times 4 to get 8. So notice how they both have a 2 in common. That's the biggest number that they both have in common. When I look at the variables, n squared is really n times n. So notice that both of those terms have an n. So that means that they have a GCF of a 2 in common as well as an n in common. Now that's not my final answer because I'm asking you to factor. So what I'm going to do is I'm going to write that GCF, and then in parentheses, I have to put what's left over. Because I started with 2 things and a subtraction sign, I should have 2 things with a subtraction sign inside the parentheses. Because 2n squared had the 2 taken out and an n taken out, you're left just with 1n. After the subtraction sign, I can ignore the 8 because that was 2 times 4. I moved the 2 to the outside, so that means the 4 is still left over. There was an n attached to that 8, but the n got moved out. So 4 is the only thing that's left over in the second term. Notice that nothing in parentheses is the same. N is very different than a 4, so that tells us that we factored everything completely. If I look at the next example, 4r squared minus 48r plus 140. Once again, I want to look for a GCF. I notice that the last number doesn't have a variable, so I'm not going to be able to get an r out of all of them. I notice that 4 is the smallest number out of those, so I'm going to see if I can get a 4 out of every single number. So let's look at this. 4 times something to get 48. Well, that's going to be 12. 4 times 12 is 48. What multiplies by 4 to get 140? Well, that's 35. So notice that they do all have a 4 in common. So I get to write the 4 on the outside, and in parentheses, I want to put what's left over. Because I started with 3 terms, I have to have 3 things in the parentheses. So the first term was a 4r squared. I took out the 4, I'm left with an r squared. I'm going to bring down that subtraction sign. Remember, 48 got broken up into 4 and 12. The 4 got moved out, so the 12 is what's left over in the middle, and there's still an r with it. I'm going to bring down that addition sign. You can ignore the 140 because it got broken up into 4 times 35. The 4 got moved out, so that means the 35 is left over. Now, this that I have in parentheses is a trinomial. When you have a squared term, the variable in the middle, and then a number at the end, we can potentially continue to factor. So remember, if there's no number in front of that squared term because we took out that GCF, I'm asking myself, what is going to multiply to the last number, but add to the number in the middle? So we're looking for numbers that multiply to a positive 35, but add to a negative 12. All right, so let's see. Numbers that multiply to 35. Well, because we're dealing with multiplying to a positive but adding to a negative, hopefully we're okay with noting that both of these numbers have to be negative. A negative times a negative is a positive, and a negative plus a negative will still be a negative. So what multiplies to 35? Well, 7 and 5. So negative 7 times negative 5 will give me that positive 35. Notice that if I add those numbers, there is that negative 12 in the middle. So those two numbers are definitely the numbers that we want to use to continue our factoring. I'm going to bring down that GCF. So 4 needs to stay a part of my final answer. But then notice that I get to break that trinomial into a binomial times a binomial. Because there was no number in front of the r squared, we get to start each of our parentheses with an r, because r times r is r squared. The numbers that we got in our chart that multiplied to the last but add to the number in the middle are going to fill in the rest of the parentheses. I don't care if you put the negative 5 first and the negative 7 second, but this would be our factored answer. Okay, last one here. We have 15n squared minus 115 plus 350. So let's see. I got to look for a GCF. Okay, 15 is the smallest number there. So I'm asking myself, can I multiply 15 times the number to get 155? So if I divided those two numbers, in your calculator, it's going to turn out to be 10.3 repeating. That means that 15 does not fit with this, and so 15 is not going to be the GCF. However, 15 actually does break up into 3 times 5. 5 is the bigger number between them. So let's see if I can get a 5 out of all of these. Well, 155 divided by 5 is going to be 31. So 5 times 31 multiplies there. If I have 350 and I divide it by 5, that's going to be 70. So notice that every single one of those numbers, they have a 5 in common. Not all of them have a variable. So the GCF is 5. And then in parentheses, I have to put the trinomial left over. So remember, you could ignore the 15 because that was 3 times 5. I took out the 5, I'm left with the 3, and I still have the n squared. I'm going to bring down that subtraction sign. I can ignore the 155 because that was 5 times 31. I took out the 5, I'm left with the 31, and there is an n in the middle. I'm going to bring down that addition sign. I can ignore the 350 because that's 5 times 70. I took out the 5 for the GCF, which means I'm left with the 70. All right, so notice that we have a trinomial. This trinomial is a little bit different than the last problem because I still have a number in front of my squared term. This is where we have to do something called guess and check. Okay, so because I still have a number in front of the n squared, I start with that number. What are two numbers that multiply to 3? Luckily for us, there is only one combination, 1 times 3. Then I move on to the last number, which is 70. I'm looking for numbers that multiply to get you 70. Now notice the signs. I need to multiply to a positive 70, but my middle term is still a negative. So it's just like the last example. What multiplies to a positive but adds to a negative? Well, that's going to be 2 negatives. So I know that all of my numbers that I list here that multiply to get me 70, I have to have 2 negatives. So let's just list all the numbers. -1 times -70, -2 times -35. Okay, 70 is not divisible by 3. 70 is not divisible by 4, but 70 is divisible by 5. That's -5 times -14. Okay, 6 won't go into it, but 7 will. So that's -7 times -10. Okay, 8 doesn't, and 9 doesn't. So that means that then we're back at 10, and so we already have that in our list. So we do have several different options here. Okay, so what I need to do is, like I said, I'm going to do this guess and check process. Okay, I'm going to leave that GCF of 5 on the outside. I'm going to create my 2 parentheses where the only way to multiply to get me that 3n squared is 1 and 3. So that's going to start me off. So I'm going to have a 1n and a 3n to start us off. And then now I'm looking at all of the options for the 70. These options here are going to be what fills in the rest of my parentheses. So now this is where the guessing comes into play. I need to guess what those numbers are because at the very end, I want it to add to -31. Okay, so let's think about some numbers here. Obviously, -1 and -70, not going to work because 70 is already bigger than 31. Same thing with the second option. 35 is already bigger than 31. So it's between the last two, -5 and -14, or -7 and -10. Okay, so when we guess, it doesn't really matter, but we can guess. So let me just do the first one. So I'm going to put -5 first and -14 second. So there's my guess, and now I have to do my check. So what I'm going to do is I'm going to multiply the outer terms of the 2 parentheses. So 1n times -14 will give me a -14n. And then I'm going to multiply the inside terms. -5 times 3 is going to give me a -15n. Now I want to combine those 2 numbers. Is -15 and -14 going to give me my middle number in the middle? Notice that this gives me a -29n. So unfortunately, that doesn't work. So it's a matter of I either need to switch those 2 numbers around or I need to try the -7 and the -10. So let's think about this. And then -5. Okay. I think what I'm going to do is I'm going to just switch the numbers. I think I'm going to try the -7 and the -10. So once again, I keep that GCF of 5 on the outside. I'm going to keep the 1n and the 3n to start us off. So let's do this. I'm going to put I'm sorry, hold on, I'm checking something. Okay, I'm going to put the 10, I'm going to put the 10 with I'm going to go in the order of how I have it numbered. So I'm going to do the -7 first and then -10 second. Okay, so once again, I'm going to check now. I did my guessing. So to check, I multiply the outside terms of the parenthesis. 1n times -10 is -10n. Then I multiply the inside terms. -7 times 3n is -21n. Notice that when I combine these numbers, I'll get that -31n that we want in the middle. So that means that I'm going to circle this whole thing with the 5 out in front because that was my GCF. And so then that would be my answer. So notice that it took me a couple of tries, and that's fine. It might take you a couple of tries as well, but that's the whole point of guess and check. Okay, so the last thing we're going to look at is how to solve by factoring. Okay, in the past, up at the top, just factoring doesn't have an equal sign. Notice none of these problems said equal anything. But when I'm asking us to solve, there's an equation. It equals 0. Okay, notice that in number 10, I already have it factored for us. n minus 6 times n plus 7. Because it's factored in equals 0, to solve for n, I just get to take each of those terms that are in parentheses. I get to set them equal to 0, and I can solve for n. So notice that means I need to add 6 over to the other side. So one of my answers is that n equals 6. And then I'm going to subtract the 7. And 0 minus 7 tells me that -7 is my other answer. When you're solving quadratics, or in this case, when you have two variables, so n squared, x squared, if it's squared, then you're going to have two answers. Okay, notice that in number 11, it's not factored for us. But everything's moved over to one side, and it says equals 0, and that's what we want to see. So because I don't have a number in front of the n squared, it's just a 1, and I don't have a variable after the 49, there is no GCF. So that just means I'm asking myself what is going to multiply to the last number, but add to the number in the middle. And once again, notice that we have another factoring problem where I want to multiply to a positive, but add to a negative. Notice that -7 times -7 multiplied to a positive 49. And if I combine those two -7s, it's going to give me my -14 in the middle. So we're going to have in two parentheses, n's are going to start us off because n times n is n squared. And we're going to have -7s finishing it out. But now this is an equation. It equals 0. So now I get to set each of those equal to 0. Well, notice that they are the exact same parentheses. So I really only have to do it once. I can take n minus 7 equal to 0, add 7 to both sides. Once again, I technically have two answers, but they're just the exact same number, n equals 7. Okay, this is what we'll continue to practice more with tomorrow, but we need to get very good at these skills. So we need to understand how to do some radicals, whether it's simplifying, adding, subtracting, multiplying, or dividing. And then we have to know how to factor because now we're going to be factored to solve.